We're going to continue discussing the preparation and reactions of alcohols. We are going to, in this video, we're going to discuss the reactions of alcohols, but first we're going to discuss a little bit more about the preparation of alcohols, about the need to protect the alcohol functional group in some cases, and about the preparation of phenols. And then we will get into reactions of alcohols, substitution and elimination. Some of this will be review. So let's look at this, the preparation of alcohols. Remember, we've been discussing the Grignard reaction, and it is so completely important that here we're going to discuss additional ways to use it. So let's pretend that you're wanting to react this molecule in a way so that you're going to functionalize this end of the molecule. So it would be excellent to be able to create a Grignard reagent here so that you could then react it and functionalize it and put these groups on the end here. So here you have put the carbon, oxygen, and the two alkyls. Here you've replaced the bromine substituent with this group, and it is set up perfectly to use a Grignard reagent. But remember, I said earlier that you must keep water and alcohols out of the Grignard reagent, because water and alcohols will react with the Grignard reagent like a shot, okay, and it will waste the Grignard reagent. If you tried to form this, this will react with itself. What will happen is this carbon that's bearing the magnesium is going to bear a very large partial negative charge, and it's going to behave as a base, and it's going to bump into another molecule of this, and it will pluck off the proton off of that other molecule. And so you will have this carbon-magnesium bond be replaced with a CH bond, and you will wind up with O minus. And as the counter ion, you'll have magnesium bromide cation. And that's not going to be useful. It's not a desirable reaction. It is a waste of a Grignard reagent, and a Grignard reagent is very expensive. And so you don't want this to happen. So how can you still carry out this without having this complication? There are ways. So you use what is called a protecting group. We have to protect this alcohol functionality so that it won't be reacted. Then, once the alcohol functionality is protected, then you can run the Grignard reaction on the other end of it. And then once you get to the product where this is still bearing the protecting group, you simply remove the protecting group. And so that's what we're going to show here. So the first thing that you do is you use the halopropanol and protect it. So you put a protecting group on this end. So you no longer have a hydroxyl group here. You have a group that can be treated to regenerate the alcohol. Okay, so this is going to be an alcohol functionality waiting to be regenerated. Right now it's protected, and it will no longer function as an alcohol while it has that protecting group on there. And so then you carry out the Grignard reaction, just like you've seen earlier. You still have the protecting group on there. And then you deprotect. You remove that protecting group and regenerate the alcohol functionality. And so that's what we're going to discuss for a few slides here. So what sort of a protecting group can you use? You can use this trimethylsilyl group. Okay, notice, so what you're doing is converting OH into O-trimethylsilyl. Okay, and that is abbreviated O-TMS, trimethylsilyl. And so the way that you get that on is by simply reacting this with trimethylsilyl chloride and triethylamine. And so what happens is the oxygen is going to have to come in and do a backside attack on silicon and displace chloride. It's like an SN2 reaction. And you're going to look at that and think, no, that can't be an SN2 reaction. This is too sterically hindered. And it would be if this were carbon, but it's not carbon. It's silicon. And silicon is much larger than carbon. And so when you have these three methyls on silicon, it's much more open than if that were carbon. And so in that case, a backside attack is possible. So let's continue, and then we're going to look at this. Now, you have your trimethylsilyl on here. You've generated your O-Si bond right here. And the counter ion is the triethyl ammonium chloride. So you've lost chloride here. You don't want chloride to be floating around. You don't want the HCl to be floating around. You don't want to have that protonated and make it be even a better leaving group where chloride could attack it and convert this into an alkyl chloride. So you have to have the triethylamine in here to pick up the proton so that won't be protonated and converted into an excellent leaving group. Okay, so this has a functionality to it, the triethylamine. So this is explaining what I just said to you a minute ago. So if this were carbon, you would not have an SN2 reaction here on T-butyl chloride. But on the trimethylsilyl chloride, the corresponding silicon compound, okay, this is the analogous silicon compound. This molecule is the same as that, except that's carbon, this is silicon. And so now, when this is silicon, silicon is much larger, and so the three methyls are more spread out. And so this is open so that you can have a backside attack, an SN2 reaction on trimethylsilyl chloride or trimethylsilyl, whatever, a trimethylsilyl group is possible. And what that will do when you have that is you will break the silicon-chlorine bond or the silicon-oxygen bond in the case of a protecting group. So let's look at this. Now, notice here you have ROTMS, so this has an oxygen, silicon, methyl, methyl, methyl. And here we have either H3O plus, so you can have, this can be protonated because this is just simply dilute acid, and then the oxygen would do the backside attack, okay? And you would have an SN2 reaction, and you would, once you've protonated oxygen, you would have an SN2 reaction here, and you would your alcohol would depart. You're going to break that silicon-oxygen bond. And here, the same thing with fluoride. Fluoride can do a backside attack on silicon bearing three methyls. And the silicon-fluorine bond is very strong. And so often you will see the fluoride used. The tributyl ammonium fluoride, tributyl ammonium fluoride is often used because when you have the tributyl ammonium, this cation is really sterically congested, and fluoride is not going to be very closely associated with the cation. So this F minus, this fluoride anion, is going to be kept away from the cationic center. So these two ions, this ion pair, will not be very closely associated. So fluoride will be bare, and that will make it a better nucleophile. And fluoride is small, and so it will be really much, much better at coming in and doing a backside attack on the trimethylsilyl group. The fact that it's small, and the fact that it's strong, and the fact that it is not associated with the counter ion all work in its favor. So now let's look at the overall reaction. So now what you do is you protect the alcohol functionality. So the oxygen comes in, does a backside attack on the trimethylsilyl. You have the chloride depart with the triethylamine picking up the proton and to occupy the HCl so that it doesn't react. Then you have, once this is protected, then you can do the Grignard reaction just as usual. So the magnesium inserts in the carbon-bromine bond, then the carbon-magnesium bond is polarized, so the carbon is bearing a partially negative charge. The carbon anion comes in, does an attack on the carbon at the carbonyl, and so you get the alkoxide, and then the alkoxide is protonated using water, and that's the product that you have. You might want to work through this, work through all those steps that I just said, work through them on paper. And so then, tributyl ammonium fluoride, remember this gives you a very bare, strong, small fluoride nucleophile, and so it will come in and do a backside attack, and you will break the silicon-oxygen bond, and then that will, and you'll have to have a workup here, you know, some source of proton, and that will form or reform the alcohol functionality up here. So you start out protecting the alcohol functionality, then you regenerate it after you've done your chemistry on the other end of the molecule. So this is a good example of that. So now, preparation of phenols. So here, what is typically used is, for this, is phosphoric acid and propene. And so then this functionalizes benzene, gives you an isopropyl group on here. And then this CH bond right here is very active because it's in conjugation with the benzene ring. And so it's a very weak bond, the carbon-hydrogen bond right here. And so it's very easy for oxygen to insert in that CH bond. Okay, so now you have a peroxide. And then what happens is, if you notice, there, look at those atoms, and you will see that those are the atoms necessary for acetone. And so those, that will become a leaving group. So what happens is a pair of electrons, it's actually the pair of electrons here, and between the pi bond that is between these two carbon atoms on the side of that peroxy group. So it attacks this oxygen. And so then the pair of electrons in the oxygen-oxygen bond moves in, forms a double bond, and then this pair of electrons moves back in so that it satisfies the positive charge temporarily generated. And so then it simply converts this molecule into phenol. You'll have that mechanism later on when you have electrophilic addition to aromatic compounds, because that's what this is. And so you'll have the mechanism then. And so this is the method that is used in that mechanism that I just gave you as a typical mechanism. Acetone is a very useful byproduct, as you know. Phenol is very useful in many chemical syntheses. Now, more on the reactions of alcohols. Tertiary alcohols are converted to alkyl halides by using HX, so you protonate the alcohol functionality. Then that gives you a great leaving group. This is water. Okay, remember OH is always going to have to be converted to a better leaving group. Here you're converting it to water. That leaves you the very stable T-butyl cation. Then the two counter ions simply collapse to give you T-butyl bromide. So the bromine anion, the bromide anion, is attacking the carbocation center. So this is obviously an SN1 reaction. Okay. Down here, whenever you have the primary or secondary alcohols, the reaction is going to be an SN2 reaction. And so still, the first step, anytime you have an organic compound in the presence of an acid, your first step is going to be protonation, just like up here. First step is protonation. Then you've converted this to a great leaving group, just like up here, except instead of a leaving group just departing, you're going to have a backside attack, an SN2 reaction, to give you the primary or secondary alkyl halide. You have had those. These reactions and these mechanisms I'll review. Now, additional reactions that you will need to know are when you use the zinc chloride along with HCl. And so in this case, what happens is the oxygen associates with the zinc. And so now up here, then the next step is going to be loss of your chloride. And then here, so that this becomes, the next step is going to be attack by chloride from your HCl. And this is a great leaving group. And it's not shown here, but it departs. And usually organic chemists don't care too much about the byproducts, except just, removing them. And so here we have chloride, which has done a backside attack. And once again, the alcohol functionality has been converted into a good leaving group. That's the common theme in all of these reactions. You have to convert the alcohol functionality into some other leaving group. Here, once again, this is a poor leaving group. We use the tosyl chloride. Oxygen does a backside attack on the tosyl. Then you have departure of chloride, and so the tosyl becomes a tosylate, and you have pyridine in here to remove some of the, remove the protons. You're going to have this becomes protonated right here. It picks up the protons so that this is not protonated by those protons and become even a better leaving group, and you lose control of the reaction. And so you have this take place, then it has to sit there and be stable long enough for you to add whatever anion it is that you want to react, and this is going to be an SN2 reaction. Notice you have a stereochemistry shown here. There's a stereochemistry, so you have one specific isomer, and then over here, notice you have inversion. So here the hydroxyl group is coming out. This reaction takes place with retention of stereochemistry because the carbon-oxygen bond is not broken. Only the oxygen-hydrogen bond is broken. And then X comes in from the back side, and so you have inversion of stereochemistry. Okay? And so you can see the R isomer becomes the S isomer. It's an SN2 reaction. Primary and secondary alcohols can be converted to alkyl halides using thionyl chloride or phosphorus tribromide. And these two reactions are somewhat similar. Once again, you're going to have pyridine up here to pick up the protons. And so the oxygen will come in for a backside attack and displace chloride. And then the chloride comes in and does a backside attack. So when oxygen becomes attached to sulfur, that is when this is converted to a better leaving group. Here, oxygen will come in and do a backside attack on phosphorus, and it becomes attached to phosphorus, and one of the bromides departs, and that comes in and does a backside attack. So when oxygen attacks phosphorus, that creates a better leaving group. So in both cases, you're, once again, converting hydroxyl into a better leaving group. Here's the mechanisms, all spread out. There's several steps in it. So basically, you're converting the hydroxyl group into a better leaving group. That's the whole point of all this. And so oxygen comes in, does a backside attack on sulfur, pair of electrons moves out onto oxygen, and so then you have this sulfur-oxygen pi bond reformed and you lose chloride. Then you have the pyridine come in, pluck off a proton, and when that happens, the oxygen is now neutral. The pair of electrons moves back onto oxygen. You no longer have an oxonium ion. You just have oxygen. Then, so this is now a great leaving group. Then you have chloride come in, do a backside attack, and this leaving group departs. Here you go. Now, the phosphorus tribromide mechanism is very similar. Oxygen comes in, does a backside attack, bromide is displaced. Then, this is now a better leaving group. The bromide that was displaced comes in, does a backside attack, the pair of electrons departs with oxygen, and so now you have, this is just simply an SN2 reaction, and you have your alkyl bromide formed. More reactions of alcohols. So now you have elimination. You know that alcohols can do elimination to give you the alkene. If you use concentrated sulfuric acid and heat, you're simply driving off the water. The tertiary alcohol does the SN1 reaction. You protonate it, the good leaving group departs. You form the carbocation, the trisubstituted, the tertiary carbocation. The pair of electrons on oxygen picks off a proton, and the double bond is formed. So this is review. You've seen this already. The E1 elimination favors the more substituted alkene. This is review. Okay, you're going to protonate that. It will depart. You'll have the carbocation formed in the tertiary position. And then when you lose the other H minus over here, when you lose the other proton over here, the pair of electrons will move in and form the double bond. And in E1 elimination, you will have the more highly substituted alkene formed. The only way that you would be able to get this as the major product is if you used a very bulky base, such as T-butoxide. So, now, if the alcohol is converted into a better leaving group, then a strong base can be used to promote the E2. So here, once again, you're converting this alcohol into the tosylate by using tosyl chloride. And then you use sodium methoxide, the strong base, to effect elimination. This is preferred by people, not necessarily energetically. And here you won't have the carbocation rearrangements, and you can control the regiochemistry by using either the Zaitsev or the Hoffman reagents, either the sterically hindered base or the less sterically hindered base. Okay, so that's the end of the first part of the reactions. In the last video, the next and final video for this chapter, we will look at more reactions of alkenes.